It's my pleasure to introduce two scientists at the forefront of causal discovery. So Professor Imme Ebert-Uphoff, who, after receiving her doctorate at Johns Hopkins, held a professorship at Georgia Tech before moving to Colorado State University in 2011. And her focus since then has been on applying machine learning methods, and in particular causal discovery techniques, to weather and climate long before it was cool and popular. Since 2019, she's also been the machine learning lead for the Institute of Research in the Atmosphere there, and is leading the CSU component of the new NSF AI Institute for Research on Trustworthy AI in Weather and Climate. So we're delighted to have her with us today. And we also have Professor Jakob Runge. So Jakob received his PhD at Potsdam Institute in 2014. And after a short stint at the Grantham Institute, he started his group at the German Space Agency in Jena, and has pioneered a number of new approaches in causal discovery, and recently started his joint position at TU Berlin. So I welcome you both to the stage, if you can, or virtual stage. If you want to undo your video, I'm not sure which of you wanted to start the presentation, but if you want to share your screen now, and please take it away when you're ready.
Yeah, Duncan, thanks a lot for the kind introduction and the invitation. Can you see?
Yeah, we see your screen.
In full screen now.
It's just loading. Looks great. Thanks, Jakob.
Great. Yeah, welcome everyone from my side. And Imme, you want to also say hello?
Welcome and pleased to be here, and love to give this with my esteemed colleague Jakob. It has been a lot of fun to prepare.
Yeah. So we put this together. We created this whole presentation together because we thought this might be a nice other way of presenting this topic, which we both have been working on for a long time now. So it's a pleasure to present it to you. So to start with, we have seen in talks here in the series, in general in the AI for Good series, a lot of ways in which AI and machine learning have moved and transformed how we do science and in engineering, and in particular in earth sciences, in the series put forward by Duncan and Philip Stier. And the slide basically shows a little bit of how methods that have been used in like object recognition in images on the left-hand side here, and how these methods in recent years have been transported to earth science tasks. So this picture is from Reichstein et al., who will actually give a talk in this series next week. And these methods put forward, among many others, of course, by Jan LeCun, Hinton, and Bengio, who received the Turing Award for this, are very capable in analyzing such data sets in terms of object recognition, in terms of video prediction, and these have been applied successfully in recent years also to climate applications. And one other example to show how there's a growing competition almost between AI methods and the physical methods or the physical models that we use in many parts of Earth system sciences is shown here. A study by Ham et al., who developed a neural net forecasting approach for El Nino Southern Oscillation. So this phenomenon might be known to many of you, which is a warming in the East Pacific, and is an important process to forecast to the next months, or here even shown to be predictable up to 18 months ahead. And this picture just shows that there's a growing skill of these data-driven methods in terms of predicting such systems. Now, the kind of slightly controversial question I want to pose here is that these purely data-driven AI methods can answer questions about what is, and they are based on learning statistical associations from the complex data. They make as little as possible assumptions about the underlying process. And that I want to put in slight contrast to what often we want to know in earth sciences. So this is a picture of the flooding that happened in Germany, kind of a more personal perspective. As a German here, of course, there's many other disasters of much more impact happening in the world. And we wish to understand the drivers of such impacts in terms of cause and effect relationships. So this is a picture that shows that such an extreme event may have different causes that may have compounding relationships. That's why I referenced this paper here. And there might be drivers that are only correlated with the extreme. And associations measuring these correlations might not be a good to look at when we ask the question of what causes these extremes, what causes one particular single extreme as an attribution framework is one question, but also in general, what causes certain processes. Another example here showing a cloud that is taken from Pierre-Gentine, and that shows a box around a cloud, which is meant to illustrate that such fine-scaled microprocesses are in general circulation models only represented on very coarse scales and which need to be parameterized. And such processes then need to be understood at a level of these parameterizations. So we need to understand in this case, for example, what are the mechanisms behind aerosol cloud interactions. And this is one particular important process that is important for projecting climate change, because these subtle mechanisms that are operating on the scale are pivotal in determining or reducing the uncertainties in projecting what our future climate will be. So with this, I hand over to Imme to study two types of causalities or introduce them.
All right, so there are two primary types of causality studies. The first one is an experimental study, and that's when we can actually do interventions. So interventions are either done in a real system, if you're so lucky that you can do that, or in physical simulation models. And experimental studies are great for causality because they support both necessary and sufficient conditions for causality, so you can actually prove causal connections. However, in climate science and earth sciences in general, it's often infeasible or very time-consuming to do that. We only have one planet, and we can't just start doing experiments, or at least more experiments than we're already doing with climate change, right? So usually we can't do experimental studies in climate and earth sciences. Next slide, please. So what we do instead is usually observational studies. And the idea here is that you're trying to learn causal relationships purely from observations and model output. You're not doing any interventions. And although those only support necessary conditions for causality, and thus only weaker statements are possible, this is still very powerful. And that's actually the topic of this talk, because this is really the bread and butter for most of earth science and causality. And so we're going to spend this talk pretty much on observational studies only. Next slide, please. So we just wanted to give you a little bit of background on who the big people are, the big groups in causal inference. So causal inference is a framework to answer causal questions from either observational or experimental data. That's all included on the slide. So Pearl already in the 1980s started to develop the theoretical framework, and that led to probabilistic graphical models, Bayesian networks, and the do calculus. Also, since the 1980s, Clark Limor started a group at CMU where he developed practical algorithms, so really making this feasible for people to actually use Pearl's theory and discover causal relationships from data. And then we also wanted to mention Angus and Immans, who won a Nobel Prize in economics, and their work was also on causality, drawing conclusions from unintended or natural experiments. Just on the right side, you see kind of a hierarchy that Pearl came up with, and I don't want to go much into detail, but let's just say that the bottom level association, that's where most machine learning work would fall, and we're trying to get kind of beyond that. Next slide, please. All right, so when you do causal inference or causal discovery, there are usually two types of tasks. You can either utilize knowledge you already have, for example, expert knowledge, to encode that in a graph. So in this case, you utilize qualitative causal knowledge, usually from experts, and you express them in directed acyclic graphs. In this case, you can include observed and also latent variables, because you're assuming you kind of know the causal relationships already. And then you use this graph to actually do inference. And secondly, you can learn actually causal graphs. You can start from scratch and say, I have no idea what my causal relationships are. I want to learn them. Can I use algorithms based on certain assumptions to do causal discovery and discover what this graph would look like just from data. And we're going to start with that, and we're going to talk later on. Jakob is also going to talk about causal inference. But first, we're just going to talk about causal discovery, so task number 2. Next slide, please. So I'm going to give you a very quick and incomplete intro to Causality 101. And that's obviously for those people new to causality. Everybody else, please take a 5-minute nap, answer your email, get a coffee, be back in 5 minutes. I don't want to bore you, but for those people who have never dealt with causality, we thought it would be good to have the basics straightened out. Next slide, please. So concept number 1, we love to use graphs as language for causal models. It's very intuitive to scientists and it's very concise. So you see an example on the bottom right here with just 3 different nodes, X, Y, and Z. And so the way this works is the variables are the nodes of the graph. And the edges between the different nodes indicate causal connections between the nodes. And if you have an arrowhead on there, the arrow always goes from cause to effect. So if you're reading the graph on the bottom right here, in this example, you see there are 3 variables, X, Y, and Z. And you see X is the cause of Y and Y is the cause of Z. And you should have a question here. And because we don't have that much time, let's just go to the next slide. I'm assuming the question you have is, well, wait a second. If X causes Y and Y causes Z, isn't an X also a cause of Z, and shouldn't we automatically have to draw an arrow from X to Z? And the answer is no, because of concept number 2. Next slide, please. So the key point is that we only want to indicate direct connections. So if you see in a graph an arrow going from X to Y, it means that X is the direct cause of Y. So in this plot, X is a direct cause of Y, Y is a direct cause of Z, and X is only an indirect cause of Z. And so we don't have an arrow from X to Z because there's no direct cause there for this particular example. And the goal of causal discovery is we want to identify only the direct connections and eliminate all the other ones and only find the direct connections. Why do we want to do that? First of all, sparsity is always good. It leads to simpler models. But secondly, and that's the more important one, is only then can you understand the effect of intervention. If I were to draw an arrow from X to Z because I believe that there's actually also direct cause from X to Z, if then I intervene in the system and I say, I'm going to just set Y to something, then if I had an arrow from X to Z, X would still be a cause of Z, right? But if I don't have this arrow, then the connection is broken. If I change Y, then X has no longer causal influence on Z. And I can only tell that by making sure that I only include the direct connections in the graph. Okay, next slide. Concept 3, directness is a relative probability. So what do I mean by that? Let's look at the toy example on the left. Let's say I have a very simplistic model somewhere in India where I'm looking at monsoon months and I look at whether there's flooding happening. So monsoon months is a direct cause of flooding in this model. However, if I also measure the amount of rain that is falling, then I put in an intermediate variable, which is rain. And so the model on the right goes from monsoon, then how much rain is there, and that determines whether there's flooding or not. So what have I done? I have made the direct connection from monsoon to flooding suddenly an indirect one by including an intermediate cause in there. What happened is, which one is right? Well, both are right, because directness is only defined relative to variables included in the model. So that's just one key thing to keep in mind. It's all relative to the variables you have in the model. Next slide, please. Concept number 4, causality is a probabilistic relationship. I mean, it's perfectly clear if I draw a picture that says monsoon months, has a causal relationship on flooding. It doesn't mean whenever we're in a monsoon months, we constantly have flooding, right? It just means it's more likely in the monsoon months, but it's not certain that we get flooding. And likewise, we can, of course, get flooding also outside of monsoon months, but it's not as common, so less likely. So in order to express this, we supplement the graph with probabilities, and that's then called a probabilistic graphical model. And if it's a directed graph, it's called a Bayesian network. Not to be confused with a Bayesian neural network. That's a very different thing. This is a Bayesian network. It's a probabilistic graphical model. When we learn these models from data, the hard part of step 1 is to identify the graph structure from the data. Once you have the graph structure and you're pretty sure what it is, to determine the probabilities afterwards, that's actually pretty easy. Next slide, please. Concept 5, and that's the last big concept. hidden common causes, also known as latent variables or confounders, they make causal discovery really challenging. And I will give you an example of why that is. Let's say you look at the model here and you say cloud cover, if there's strong cloud cover, my amount of UV is lower and my chance of rain is higher, okay? So clearly a cloud cover has causal effect on both the amount of UV and the chance of rain. Okay, let's say now I want to have a new model and for some reason I can't measure cloud cover, so I'm taking it out of my model and I only have 2 variables left. Suddenly I cannot, with my current language that I introduced, I cannot express things well anymore, because neither is the low amount of UV causing the high chance of rain, nor the other way around. So the problem is that now suddenly, with the language I introduced, I cannot express the causal relationships properly. So there's 3 alternatives to dealing with latent variables. Number 1 is just ensure to always include all latent variables in the model. You go to the top, you introduce cloud cover, life is good. Usually you can't do that in earth science because there's so many latent variables that you don't even know about or you can't measure, that quite often number 1 is impossible. Number 2 is, well, I can say that, well, I can consider the errors that I get only as hypotheses because they might actually be caused by an absence of a latent variable that I didn't include in the model. But I can always say an absence of errors means an absence of causality. I just can't say that the presence of an error really means causality. And we'll get more into that later. And thirdly, I can use different algorithms that actually use a slightly different language that have additional error symbols to actually also find some of the latent variables, but they usually still tend to be statistically fragile. So we don't use them as much as other ones. Next slide, please. So we've talked a lot about trying to remove edges. How can we do that? Well, we can use conditional independence relationships for that. Because if you look at the graph on top, x, y, z, they're everything connected. If we're asking whether we can eliminate the edge between x and z, that's equivalent to asking, is there a direct connection between x and z? It's also equivalent to saying, is x conditionally independent of z given y? And it's equivalent to saying, is the probability of x given yz approximately the same as the probability of x given y? In other words, does z have an influence there if y is given? So we usually use number 3, which is a conditional independence test. So now we know that if x is conditionally independent of z given y, we can eliminate that edge. And many statistical tests, of course, exist for testing conditional independence. This leads us to, next slide, our first causal discovery algorithm. It's called the BC algorithm, and as I say on the bottom line there, it's called the BC algorithm named after Peter Spirtus and Clark Limor, who invented this algorithm. And so they just used the first letters of their first names, probably not realizing how often this algorithm would be used. So the basic algorithm works like this. You start with your nodes of your graphs as your observed variables. You have your data set. You look at all your observed variables. You make each one a separate node. You start with a fully connected graph, so you're saying everything is connected to everything else. You eliminate as many edges as possible using conditional independence tests. And if you do them in a certain order, it's even very tractable. And then you establish error directions afterwards using constraints from additional independence tests or temporal constraints. And I won't go into that here because we don't have the time, but it's basically an elimination procedure. And whatever edges are left after you eliminated as many as you could are the potential causal connections, so the causal hypotheses that are left. Why only potential? Well, we talked about this before, because some of the connection might actually be due to latent variables that I didn't know about. And so the point is, what is left at the end is a set of all the connections that could be in the system, but we've eliminated lots of other ones that are not there. Okay, next slide, please. With that, I'll turn it back over to Jakob.
Thanks a lot for this introduction. So that sets the basis of learning causal relations, and we've seen that there were no time series really involved, but that's often a form in which data comes in earth sciences. We have dynamical processes, a dynamical system, not always, of course, but that is frequently the case. And these can still be represented in this graphical form. So you might represent the different time steps at which these processes occur at different nodes. So you just unfold one node at different instances of time, and then can represent them in the same way with these causal networks, and might assume that these are due to stationarity. Then this segment of the graph we see is repeated infinitely. Now, time series come with more particular challenges. So as time series inherently often are autocorrelated, this leads to problems of a statistical nature in estimating these conditional independencies. On the other hand, we have as an advantage also these time lags that give us information on when a causal relation occurs, and that can be learned in this way. We still might have contemporaneous links between two variables, and they can still be represented in this way and treated in the way that you've seen above in Imme's part. And we may also need to deal with latent variables. And just briefly showing one slide on potential ways to address this that me and my group developed in the past. So one thing to address these challenges of autocorrelation is to use particular form of conditional independence test in terms of what we condition on. And that is here shown in two phases: PC1 phase, which is actually an extension of this PC algorithm we've seen before, and then another phase that uses certain independence tests that are better adapted to autocorrelated data. And such algorithms then allow to uncover, to reconstruct such graphical structure, including instantaneous relations. Now, these methods still assume that there is no unobserved variables. And recently in my group, we have developed also an algorithm that tries to represent these unobserved variables and estimate these graphs. So when you have an unobserved variable here, for example, that causes x1 and x3, then a way to represent that in a graph is here by such a bidirected arrow. And in fact, there is, under certain assumptions, ways to estimate such graph objects from the data. And especially because of these autocorrelations, this is actually much better to achieve than in the non-time series case. So these algorithms exist, but there are, of course, also others that deal with time series or non-time series and help us to discover causal structure. So in summary, the point I want to make here is a point of caution that already was made by Imme, namely that the causal interpretation of such graph has to take into account the assumptions that underlie the methods. And in the case of this PC algorithm, for example, these are most importantly the Markov and faithfulness assumption, which essentially relate dependencies in the underlying graph to statistical relations between the nodes. And these conditional independence tests make use of these to uncover what constraints this imposes on the causal relations. And of course, the other assumption that I mentioned, some methods assume no unobserved variables, but that's not necessarily the case. So that there are methods that can make stronger statements about this, but making less assumptions is always something that will lead to less informative results. The more stronger assumptions you're willing to make, or that you can make based on your system, the more you can learn about the data. This is kind of the trade-off we always have. And to mention that, what also Imme was saying, that we think that this tools set has been underutilized so far in the geosciences, where often we still see correlation and regression being used, and then still trying to argue about causal relationships. And we believe that using these tools more can help to generate and test hypotheses and come up and discuss them with further methods then. So it's always something that you have to interpret with caution, giving the assumptions into discussing the assumptions underlying these methods. All right, so that was the topic of learning causal graphs, which is a more challenging topic than the topic of given a causal graph, we want to estimate causal effects. So what exactly do I mean here? So this assumes that we have qualitative knowledge about the underlying graph structure. And Imme already showed this graph where we see x causing y, and then there's some variable L, which denotes a latent and unobserved variable. So we cannot get any data, we cannot use it, we cannot build a statistical model for L. And we have some observed variable Z, for example. And our target quantity that was the quantity introduced by Pearl, if this probability of y given do x equal to some small x, and that is the distribution of y, which is called the interventional distribution, if you intervene in x and set it to some value. And based on that, you can define causal effects, because that is really the change in the distribution that you get by intervening. But now we cannot intervene. That's the whole topic of this talk, that we have only observational data. And the target of this part that has been put forward by Pearl a lot is, given such a graph, how can we come up with some way of framing, of expressing this target causal quantity in terms of the observational distribution? So, for example, here, that theory would tell us, well, you need to account for, you need to control for z here. That is a confounder. That is a variable that we can use to estimate the causal effect. So this would be the expression in terms of the observational distribution, which uses this conditional density of y given x and z weighted by these z values. And this brings us nearer to the goal of estimating causal effects. For example, such target quantities based purely on the observational data can then be expressed with, for example, machine learning tools. For example, the expected value of y can be expressed by fitting some function, which can be very complex and achieved by deep and machine learning tools in general, and then some weighting factor, which accounts for this quantity here. So to put it in a little practical example by some toy model data, suppose we have some x and y here generated by this model, and I generate interventional data here. I set x to these values and then estimate what value would I get with y. I might perform experiments. And the causal effect, if this is a linear relationship, is then illustrated by this black line here. Now, what if I do not take into account this theory and this way of confounding, of controlling for z, but just fit a regression model of y on x and just ignore this? Well, then I would get something like a regression line that is not consistent with the causal effect. You might get a too large effect, or a too large of a slope, or too small of a slope. It depends on how the confounding exactly looks like. But you will not measure the causal effect underlying. On the other hand, if you have this linear assumption here and you fit a multiple regression model, which just takes x and z into the equation, and then the coefficient in front of the x would correspond to the causal effect. And then you would say that this causal effect can be identified. And this is exactly what is facilitated by this theory. It might not always look that simple. There are more complex approaches to represent the target quantity in terms of the observational distribution. And that whole theory is actually complete. So given such a graph, it will tell you whether or not an effect can be identified or not. So for example, if also z is unobserved, it's impossible to do so. And that's what is an achievement of Pearl and many of his PhD students and other collaborators. And in contribution to this, that is based on, well, sometimes, for example, for this more complex graph, you may have more than one way of controlling for confounding. And then the question arises, well, which of these sets should I choose? I can choose only Z1, that would be sufficient, but also Z2 and Z3. And in recent work, we looked at, well, how can we do this optimally to get the lowest error that is possible for such an estimation? Okay, so we talked about these two frameworks now, and they come from a theoretical point of view and have been applied to different disciplines. And in climate science, we have particular challenges that method developers partially focus on, partially still have to work on. And there's a paper, a perspective paper recently with many co-authors, where we try to distill these challenges out of the literature and look at different problems that we have. And I won't go through all of them, but just to say, we already mentioned autocorrelation, time delays. We have nonlinear processes acting there. The climate system is in the weather regime chaotic and has a state dependence there that needs to be taken into account. We may have different time scales, be it that we have extreme value distributions operating in the climate system. We may have these noise distributions. We may have slow and fast timescales of oceanic processes interacting with atmospheric dynamics operating on faster timescales. How can we represent these different timescales better? We have a fundamental problem, which I call variable extraction here. So we often have just satellite data as our underlying observational data set, while the processes of interest that we have may be quantities that are kind of latent in a sense, but we have many tools to reconstruct them. So dimension reduction techniques, for example, are being used to reconstruct indices in the climate system. Just if you have a large amount of data, but your underlying processes are latent and there's some kind of expert knowledge that defines these. But it needs to be taken into account in these frameworks. We discussed unobserved variables, which can partially be addressed. We have problems of time subsampling. If a satellite only covers a certain patch of the Earth every 11 days or so, then we have a process that it's sampled only at particular times, while the underlying causal relations might be much more frequent. We have time aggregation. Yeah,
Jakob. So I've been tracking the question of Q&A, and I think this would be a good point to just take a few of them. If I can just ask you the questions, because you probably can't see them. So one question is, regarding identifying causal effects in time series data, how much data is needed to sufficiently run these algorithms? Are we talking about multiple decades with hourly data, or would annual time series with daily data be sufficient? And why don't you take a crack at it first, and I give you an answer to.
Right. So very good question. So it usually really is not so much about how many days or so have I measured, but it's about how many independent samples I have for measuring, for example, condition independence test. It's always about the sample size that you would need to be large enough is often not the number of days you have, because of autocorrelation, you get a lot of dependencies in the data, but it's rather really depending on the process that you look at. If there's many large scale processes or long time scale processes, you might need more data than for a more noisy, a more stochastic process. So that's something that really depends on the different application.
Okay. And I would just add, if people come to me and say, well, I have monthly data from like the last 50 years, that's 600 data samples. I cannot do that much with that. So my first question is always, can we not do anything with daily data? But of course, that is a different process, right? So I would just quickly ask one more question to Jakob, and then we will move on and take so many questions at the end. So there was one related question. Can you speak to the maximum number of variables which an algorithm like the PCMCI could handle in a favorable situation?
Yeah, again, that depends on, for example, if your causal relations are very weak, and then these algorithms, they try to really efficiently deal with large amounts of data. That's how the PC algorithm is already structured, not just for computational reasons, but for statistical reasons to do less tests, which lowers your power of detecting these. It depends really on the application. It's hard to make a definite argument, but you can look in the papers. There are a lot of studies there on checking how many variables it can account for, how many time lags, but it depends. It currently has not been evaluated, for example, for thousands or so, but depends to be seen if you ask that. And actually, Imme will have an application where it deals with 1,000 and it works computationally, and it depends on the strength of your relations, what you are able to estimate then. So more on that in the application.
Yes, perfect.
So with that, I think we've covered already the problem of sample size, dimensionality here, and other problems, of course, that are challenging our measurement errors. We may have other things like dating uncertainties in the paleo community, which are yet to be really found to be represented in data. All of this is to say that actually it requires close collaboration, because many of these challenges are not much on the screen of method developers that often tend to stick to their machine learning conferences, and we need more exchange. That is a goal of this paper, but in general, we really need close exchange in collaborations with method developers and earth scientists to tackle these challenges that are of eminent importance. Okay, moving forward to application use cases, I will start with a few, and then we'll give it back to Imme. So there are many, of course. The most obvious ones are that you can learn causal graphs to understand mechanisms. That's what I set out in the beginning of this talk as a goal. And just getting a qualitative graph using causal discovery, maybe one goal. And the second one, following up on Pearl's work, would be to quantify such mechanisms. And that may involve to say how strong is one particular effect, one link, the strength of a link. It may be mediation analysis. What is the indirect effect of one variable on another, which may still be causal, as mentioned by Imme in the first slides. Or you may do mediation analysis in terms of what intermediate variable is important for mediating a causal effect. All these can foster an understanding of the process and a better understanding of the underlying physics that we wish to address. Other than that, as a separate topic, and that was on the second slide, causally robust forecasting. We've seen this forecast of ENSO, which was achieved by deep learning. And you can now argue, well, maybe we can do a more causally robust forecasting if we learn causal relations, which give rise to more robust predictions. For example, if a purely associational model takes as an input variable some other variable that is actually unrelated to the target process, and something happens in that variable that would not change our forecast in principle, but it would change the forecast of this model. So restricting your forecast model to causal relations may be very helpful, and that is covered in several publications, for example, here. And then detection and attribution of extreme events is yet another scope. It's not purely based on observational data, and that can be framed in terms of causal inference, as has been done by Hannah and Pearl and others in this paper, which really tries to connect the use of interventional data, of climate model data output, with the causal framework to address questions like, what's the probability of a certain event to occur? And finally, I mentioned that we have these tools of physical climate models, which is maybe different from many other fields where we don't have so much physical knowledge. And a large part of the talks in the AI for Good series was actually also about how to do hybrid modeling between physical and climate models, how to use deep learning or machine learning in a smart way to speed up physical modeling. And the other topic I will discuss now is evaluating climate models and constraining projections. But before that, coming to a more fundamental problem that was mentioned on the challenges slide. So we have this satellite data often that gives us a high dimensionality and a redundancy. So two grid locations in the tropical Pacific or so will have almost the same temperature. There's a lot of spatial correlation between two nodes. And you might argue that, well, I don't want to know the causal relations of this particular node, but rather I mentioned to reconstruct some emergent property. If you're interested, it depends on the research question. So this figure here shows kind of a pipeline starting from these gridded data. You might do some type of dimension reduction to come up with more regionally representatives of particular processes, and then run your causal discovery on these, and run your mediation or your causal link strength analysis on this network. And you can also do more aggregate analysis then. So as an example, in this paper, we used Varimax, which is a particular form of PCA with a different optimization criterion, to reconstruct a number of processes that represent the sea level pressure field at the surface here. And then run causal discovery on these surface pressure modes to uncover a causal network. And here showing just a subgraph to illustrate, well, here we look for in what ways the East Pacific pressure influences the pressure system next to India, which is a good predictor for the Indian monsoon rainfall, and in what pathways are there that of influence. And one particular finding is here that the pressure over the Indonesian archipelago is the one that dominantly mediates this, rather than more direct influences here, or the one through the Chinese land. And the last point here of this importance of nodes is Well, coming from a complex systems point of view, you might think of, well, which of these processes up here is most dominantly in causing others, and that's the outer ring color here, and which one is most susceptible, which one is most influenced by other nodes. This is the inner node color, and the number of nodes affected is the size of the radius. So this is kind of a complex network perspective on using these causal networks. And finally, dimension reduction here done by Varimax can also be achieved by deep learning methods, such as here, where we try to find common regions by an autoencoder that represents them in a more succinct form and also is able to cover nonlinear relations. All right, what I mentioned before is how can we use these tools to improve our physical climate models, which are still the basis of our predictions of the climate in 100 years. We would not trust a pure data-driven AI model to give us this information. And the idea here is we have real-world processes, the observations, of course, that give rise to observed data. And we have the models, and maybe 4 different models giving slightly different evaluations or slightly different values for here gross primary production in this picture. And one can then compare, or should compare, the methods, the models and the observational data and how well they represent these processes given the absolute values, for example. But another way, or a complementary way, is to, well, let's look at the dynamics. Let's look at how the dynamics are within each model by reconstructing causal relations between different variables here, which need to be defined in different ways. And then we have different networks for these different models and can compare these to the observed causal network and do what we call a causal model evaluation in this work by Per Novak and myself. And this enables us to compare the dynamics of the processes as another way to study which of these models can be used, for example, for climate model projections. So then that can be used, and that needs to be carefully done in making more assumptions about whether we would trust models that well represent the dynamical processes now in better forecasting, in better projecting our future climate. So that's a current active area of research. And another way how this has been used is here by Baker et al. And by Dorrit Hammerling in work where you look rather at, well, you have maybe a climate model and you change something in the code and you want to check the consistency, whether you screwed something up in the model or if you compress data, and whether you still in the compressed data capture that the processes the data still has the same dynamical relations. And also here, the similar idea has been used in this work. So there's many ways how causal networks can be used as a comparison metric. And finally, before we move on to Imme's talks, is this topic that will also be covered next week and has been covered in earlier talks. So I just mention it here because it is a nice way of how causal inference AI goes together with climate modeling. And that is here used in a way to better parameterize these subgrid scale processes. So I mentioned the cloud in the beginning, which has to be parameterized because it's too finely grained to resolve it fully in a climate model. And this parameterization depends on, for example, a deep learning model, which depends on a certain inputs. And to better capture the causal relations inside that parameterization, one can try to first do a causal discovery to find out which variables are actually the ones that cause these. And that can be learned on highly resolved models or also on observational data in principle, put together with physical constraints, all of which have been discussed in other talks, can be a new way of hybrid modeling. And with this, I go over to Imme.
All right, so I have a few more applications that come from our group's work. So the first one, I just wanted to show you again, a very simple model where we look at the effect of Arctic temperature on the jet stream. And this was really motivated by Elizabeth Barnes, who is a climate scientist asking, well, could we do this kind of analysis? So we set out together to do some causality analysis. And we developed 2 different models, one just between Arctic temperature and the speed of the jet stream, and one between Arctic temperature and the latitude of the jet stream. And the key thing on this slide is just, look, there are only two variables, but they're called the feedback loops. But we can deal with that because we can use the time series approach that was discussed by Jakob earlier with the PCMCI, where you add like variables to the model and you build the model including those, and then you can actually get the time lags and everything, and you can see whether the relationship is positive or negative. So for example, in this case, the way to read the summary graph is that Arctic temperature turns out within 5 days, if Arctic temperature goes up, 5 days later, jet speed goes up. And then it takes another 15 to 20 days, and the increased jet speed will actually increase Arctic temperature. So it's a positively reinforcing feedback loop. And I won't go into the details here as to the interpretation from a climate science perspective, but the key point is just, you can get with these causal analysis, you can get the time scales, you can really kind of figure out, okay, if there is a causal relationship, it's 15 to 20 days later. And it's still then a question for the domain science to go back and say, okay, what mechanisms explain that, etc. Next slide, please. With that, I'm jumping in one of my favorite topics, which is how you deal with spatially distributed systems. Say you have a whole grid around the globe, and I'm just first citing here Jakob's paper from before to show you approach number one. So what Jakob and his group did was they took in panel A, they took the system, which was the time series on the globe. And then the first step they did was to do some dimensionality reduction. So you reduce it to a small number of modes over here, which then in C you use as the nodes of your causal network. So you brought it down into a relatively small number of variables, which are now far apart on the globe. Okay, next slide, please. So a different approach that we've been taking, and this was actually 10 years ago, believe it or not, we wanted to track information flow in the atmosphere. So we wanted to keep all of the different nodes from the grid and just ask the question, okay, which ones interact with each other? And so approach two is to really use all nodes from the original global grid. But the challenge, and I will show you on the next slide how challenging that is to choose a good grid for this. Because if you aren't careful with choosing a good grid, you actually get a lot of artifacts from the grid. And I will tell you in a second how that happens. And so just the results, again, we just want to show you what you can do with these tools. So in this case, we have thousands of variables because we have all these grid points, and we also have some select copies in the causal analysis because we're doing a temporal analysis as well. And so what you see is basically the zero day delay, that's basically due to slow processes on diffusion. And on the right side, you actually see advection processes coming out. So this is a causal flow within 1 day. And all we did was just putting in temporal sequences of 500 millibar geopotential height at all these different points. We interpolated at these grid points, which we call Fekete points, which are equally spaced around the globe. And then we just applied the PC algorithm with a few little variations on it and got these kind of graphs, which now can help us to track information flow in the atmosphere. And that's especially key because we can apply that also to model data. So we can see now, if we take, say, a climate model and we look at the output and run this again, we can see how that information flow is changing in a changing climate. Next slide, please. So this is just a warning that you really have to be careful with your grid. So when we first set out, we used something that's commonly used in earth sciences, which is called an equal area grid. And that's just I don't want to go into too much detail, but what you're getting is basically a grid that has some hexagons in some places and straight lines in other places. And what happens is if you set up your causality program and you just say, okay, find me the nodes that interact the most with each other. If your grid points are not equally distributed on the globe, it is heavily biased towards always connecting the nodes that are closest to each other in space. So what you're getting on the left over here is the result of, if you use a standard equal area grid, it looks as if in some part of the globe, like over Africa, causal connections go straight, and on the back of the globe, they go in hexagons, which I think we all can certainly say is not really the case. What is the case if you use a Fekete grid on the right-hand side, you will see that you have diffusion processes that are pretty equally around the globe, but then you have the advection you see on the very right panel. So the key point, just the take-home message is, be really careful about how you choose your grid if you do anything of that sort. All right, next slide, please. Approach number 3 to spatially distributed systems, and that goes also towards the direction of one of the questions we had in the Q&A, is what if you actually want to track interactions between processes occurring at different scales? So if you want to do that, one way to do that is that you actually transform all of your data into spectral space. So you take all of your time series data around the globe, and you just transform it into the coefficients of the spectral decomposition. And since we're dealing with the sphere here, functions on the sphere, we use spherical harmonics rather than Fourier transform or wavelets or something of that sort. So you transfer everything into spherical harmonic space. You select your nodes to be the real and imaginary coefficients of the spherical harmonic decomposition. And then you apply your causal discovery, which is listed here as structural learning. And you get a graph of dependencies between different scales, spatial scales and also temporal scales. So that is one way to deal with, if you're trying to figure out really interactions between different scales. And the results are on this paper. Next slide, please. So with that, we have our take-home message, and then we just have a few advertisements, and then we wrap it up and take questions. And Jakob and I would be here for quite some time longer, so if you have more questions, we are willing to go beyond the full hour. Jakob, you want to take this one?
Yes. So to a message to take home here would be that we hope to have conveyed to you the idea of using causal inference as a framework to answer causal questions from empirical data. That was the beginning slide of machine learning AI, if it's purely data-driven, being able to distill associations, while if you're willing to use assumptions, you can make more causal statements about learn them from data. We discussed two settings. Firstly, what if you have qualitative knowledge, which is often available in earth sciences? Then you can use this qualitative graphs, which encode the assumptions you make about the underlying system, to then be able to quantitatively determine causal effects in the data. That was this mediation analysis and these kinds of studies. And the other one is when you do not have so much knowledge about, you just have your nodes basically defined based on dimension reduction or whatever, and then want to learn the links, want to learn the causal graph. And then, of course, as a next step, you can again do this quantitative estimation of the strength of links and so on. So these are two different tasks that we have. I hope we have made the point that this reasoning requires assumptions for causal discovery, even these assumptions like Markov and faithfulness, or maybe causal sufficiency, to be able to reconstruct causal graphs from data. There's no free lunch, of course, as always. And this is an important point that is enabling it to go beyond purely questions of what is, to answer questions of what if about the data, purely from the data. And we would argue that causal inference, or it's been argued in Pearl, for example, also, that causal inference well complements AI and machine learning on complex data sets. Machine learning having this success in dealing with complex images, with complex data sets in climate, then transporting this idea, and causal inference providing a theoretical founding to apply these, be it in the form of defining graphs on which you base your complex machine learning estimation pipeline, or be it in ways that machine learning also helps to build better independence tests, for example. And this note of caution that the primary goal of causal discovery is really to generate hypotheses for further investigation. So these causal statements have to be put into the context of the assumptions. And you might have a graph in your paper, discuss what you get with this graph regarding causal effects. And then maybe there's an alternative hypothesis about this graph generated from causal discovery. And then you discuss, okay, what comes out then? And therefore you transparently communicate to the readership what are your assumptions, rather than hiding them if you do a regression somewhere and then still writing about influential like influences, or using causal language in your work. And there's lots of opportunity for this in earth sciences to come up with methods that have been applied elsewhere and adapt them to earth sciences. So there's lots of ways this can be done, and there's lots of ways to cooperate on this. And some works here in the books that are partially theoretical and partially more accessible, and review papers, of course, will help you in that endeavor. and also the software, which we list here, and it's an incomplete list, but there's many ways. This is by the CMU people, by myself, in R. You can have it in the different forms, and there's more and more packages that come out to help you in this task. Imme, you want to say another take home, or we move to the ads?
No, I just want to say we should keep on moving. Oh, I am?
No, we don't hear you loud and clear.
Okay, so I just want to say we should keep moving and just do the advertisement slides, like 10 seconds a piece, and then move on to questions, I think.
Right. Okay, one slide here is, there's actually a journal, Environmental Data Science, where Imme is in the advisory board, and I'm in the editorial team, and Claire Monteleone was founding editor-in-chief, and that is a journal to bring together these communities of AI and environmental science more broadly. So that's a venue where you can publish such works. And that from my side, that's a picture of my group, and we have open postdoc positions. If you want to develop methods with earth sciences as a background application, then you are invited to apply here. You can see on my website the ads. Another ad.
Yep, just go to this to look up an open position that we have and apply by February 7th.
All right, and with that, we have one last.
With that, yeah, let's just keep on moving, because we will post those slides online anyway, so people can look at that in more detail. Let's just go to the last slide and answer more questions.
Yes, thanks a lot.
Fantastic. Well, thanks a lot to both of you for really not only a great talk, but a great tutorial and introduction to all these causal methods and discovery theories behind them. So that's really great. There's lots of discussions already in the Q&A. So I think we'll just pick some of the few points raised. So a question that came up earlier is sort of when you want to find these causal effects in time series data, how much data do you need? So do you need multiple decades with hourly data? Would annual time series with daily data be sufficient? So that's a question by Robert Ladwig.
Yeah, we covered it partially, right, before. Like, it really depends on the process. If there's long time scales, like there's a decadal variation in your time series, you might need. I'm trying to go to this slide, because just like if you have a process like here in the panel 5, and you have only a segment of data covering the last 20% or so, where there's a very slowly moving quantity, like oceanic process or so, then if you just use that sample, then your causal relations might be not reliably estimable from the data. If you, on the other hand, have a very stochastic process, that may be the case. So what I often think of is use a toy model to analyze how reliable a method is, and construct your toy model to represent the challenges you have in your data, such that you can get a kind of a glimpse of whether the method can be applied. Or you will find this out in uncertainty quantification. You run these algorithms on different subsets and then see whether the graph is completely different, and that gives you a glimpse of the estimation variance and whether or not you can actually apply it. So sliding window analysis can be done for that, or Imme has some other additions.
I will give you my short answer. When people ask me, how many data points do you need? For some reason, whenever I have in the thousands, I'm fine. Whenever I have below 1,000, I can't do a whole lot. I mean, of course, it depends on the number of variables you have in the system and all that stuff. But for me, the magic number is I want to have a few thousand samples. So usually that means daily data. It doesn't have to be hourly, but usually I like to work with daily data. If it's monthly, it gets really hard. Just because we only have like 600 samples in 50 years. So that's my guideline. I need thousands of samples to do something for my applications.
It depends. With fewer samples or so, you might only be able to measure strong effects, right? Yeah.
Right. And that's one thing we didn't mention that much, is that you get the strongest connections only with these approaches. The not so strong ones usually disappear with the noise, right? They're all modeled in. So you only get the strongest ones. Almost always, for each node, no matter how many other variables I have, I don't find more than like 3 or 4 connections for each node, because the rest of them just fizzle out with noise.
So, Imme, that brings us nicely onto this question from Jose Maria Habas, that how do we evaluate these networks, right? And this is something I've struggled with myself. Is okay, the algorithm, this great code. Sometimes you can turn the handle and it gives you an answer, and how what do you do then? What's the next step in kind of validating and understanding these graphs?
Yeah. So I think there are two answers to that. One, just like in machine learning, you need benchmark sets. So we actually developed one benchmark set, and I can put that in the chat or something in a moment. But we have a synthetic data set where we just have an infection diffusion set going on. And we know exactly, because we're simulating the data, we can tweak how much noise we want, and we can just see then what happens with different grids, with different everything. And we've used that to tune and understand the reliability of our methods. So that's one way. And the other one, if you have real world data, it's the only thing you can do is, it usually works like this. You come up with an analysis. Once you get an analysis that seems to make sense, you really sit down with the domain scientist who knows the area, who would say, oh yeah, this makes sense because we've seen it in this publication and we know this mechanism. This makes sense. Oh, this doesn't make sense. Maybe that's a new hypothesis. Let's look at it. So kind of in the real world, you're usually hoping that most of them is already known, but that there's something unknown in there that will actually intrigue the climate scientists to look into. And that's, I think for me, that's the power, is hypothesis generation of all the causal relationships we haven't seen yet. Bring it down to a small number that they can investigate.
Right.
Again, we can't prove causal connections if we only have observational data, but we can bring it down to a small number of hypotheses, and then, yeah. But yeah, it's kind of subjective, right? If you're talking to climate scientists, it's like, yeah, this makes sense, this doesn't. That's the old problem. But I will, maybe Jakob takes a stab at this question, and meanwhile, I will find the benchmark paper and put it in there.
Yeah, one addition is like to conduct analysis careful in checking the parameter of the method to see what is the variability that you get when you change those.
Right.
And to also conduct analysis, for example, in a way that you don't add all variables at once, but you, for example, start with 2 variables and then add other potential confounders and see how the network changes, and whether that new node that you put into your analysis was a confounder of some variables and led to some links vanishing or so. So that is a way to do that carefully, and to run really uncertainty estimation. And if you use, for example, Bayesian score-based methods, you get a handle of that in a Bayesian framework. If you run these here, you can run them iteratively on different subsets of the data, for example, to get a handle on that. There's different ways to try to quantify uncertainty.
Yeah. So I think, yeah, in that framing, it's more of a discovery tool, and you use it collaboratively with domain experts to kind of understand and explore the data. Yeah, that's great.
And I can't emphasize enough that you shouldn't just embark the domain scientists at the end. At every step of the process, every time I don't talk weekly to them, I'm going off in the wrong direction. It's like this, every week you have to talk, or whenever you're trying to make progress, from the very beginning, from how you set up your problem, how you pre-process your data, because otherwise you need the domain scientists to tell you how to pre-process the data so that the causal relationships are as strong in the data as possible. You want to bring out the relationships. Maybe you do anomalies instead of the original data, etc. And maybe you only want to use the summer, not the winter, because they know the signals are stronger, which I don't possibly know.
Yeah, that's a good point. Thank you.
Yeah. And bringing people together is exactly what we're trying to do here. So that's good. There's a question by Ken Takahashi, which is it practical to test for causality of a large number of time series, for example, gridded data? And I'll sneak in a follow-up question once you answer that one.
I would hope that we showed that in some of our applications. So we sometimes have thousands of variables, and we were able to find meaningful relationships there.
Okay, that's great. So my follow-up question to this, and I've hinted at that before when we had a chat already, is sort of these dimensionality reduction methods obviously work well for these large-scale atmospheric features and so on. But quite often, many of the uncertain climate processes, say cloud feedback, they're really on the local scale. And so the question I have is really, what do we do about these sort of incomplete time series where we can't reduce things in dimensionality? So we might work on gridded or even ungridded satellite data, But in particular, this satellite data tends to be intermittent because a sun-synchronous satellite gives you one measurement a day of all the variables you want, but you don't get a complete time series to look into this. Do you have any further thoughts on causal methods in this context?
So I wonder whether you mean challenge number 9 here, that you have some x and y, and only every second value, like every second day, you get an estimate of the variable, and combined with the challenge that there's some unobserved variables that you don't get. So that's often what you get. Like, you develop a method for one challenge, and then you ask some practitioner, and they don't have this one challenge example for you, but they have an example with 6 challenges, and you say, wait, I can't put so much in my method paper, and that's what I frequently get. Maybe that's the answer, unfortunately.
Well, it's even a bit worse in the sense that there's no real time series as such, because sort of the clouds on 2 consecutive days are typically independent, but both of them have a strong correlation with another variable.
Yeah. So partially this ends up really using your expert knowledge on whether, given that some stuff is latent and unobserved, whether you are able to reconstruct it in some way. And then the variables then you consider that you have reconstructed, they are the ones that you then deal with and run causal discovery. So you try to first explicitly reconstruct them, which is one way to address this. The other is maybe there's unobserved variables and we leave them unobserved and try to deal with these more complicated graph objects with these bidirected edges to discover this, to not explicitly model them. But I mean, we in studies have this issue, right, that the X that we want to know whether it causes Y is partially unobserved. So that's kind of a non-starter in a way for causal inference if the variable you want to measure whether it has an effect is not even measured. So there's no magic tool to overcome that fundamentally. So you make more assumptions. Either you reconstruct it from proxies, and that can be done, right? Deep learning is a tool for that, for example. And then you have it explicitly and can run causal analysis. And that is an interesting topic that we actually do work on. Yeah. Great, thanks.
There was a couple of linked questions that I wanted to touch on. So the first one in this, well, I'll start with the more general one. Is it better to include more variables as possible, or eliminate ones that you think are less relevant? And linked to that is, what counts as a variable? How do you decide whether to include solar zenith angle or time of day or accumulated kind of surface irradiation?
Yeah, I mean, some aspect of this is of a statistical nature, and some is you change the hypothesis. Like if you add the seasonal cycle as a node to your data, then that will be removed as a confounder in, for example, inside the PC algorithm. That's one way. But you can also explicitly use anomalies. You just subtract it beforehand,
right? Which
is another way of estimating that confounder. So there's 2 different ways to do that. But they have different hypotheses underlying. And then adding variables, well, if you know that some variables are irrelevant, then you shouldn't include them, even though these algorithms are smart in a way that they test first whether there's any dependence, and if there's none with any of the other variables, then you can remove it. That's the underlying assumption. If there's no statistical dependency, there cannot be a causal relation, which is an assumption where you can construct counterexamples to. But these algorithms are usually smart in figuring that out. So it often might not harm. It depends on the algorithm. If you have a Bayesian score learning method that will try to go over all possible graphs among your set of variables, and you put in too many nodes, that explodes computationally.
Yeah.
So it might be a computational issue and a statistical issue, and that is, these algorithms try to handle that.
Imme, you wanted to?
Right. So I have a few comments on that as well. So the first question was, should you include variables that you think are not as important? I would always start out with the simplest model. I mean, you start out with the science question, right? You don't start out with the data, you start out with the science question.
Right.
And then it's the tricky part. How do you, given that we don't have, for some things we only have proxies, some things are redundant, et cetera, how do you translate the science question you have into the causality setup? And as you saw before, for example, with the grid where we just said, well, which connections are the closest? You have to be very careful because the causal discovery algorithm will find the things that are most closely related to each other. But we really translated the question the wrong way because we didn't space the grid points out correctly. So we biased everything. The same thing can happen if you have lots of redundant variables, or then suddenly the impact of different things can be split across those variables, so it doesn't seem as strong because you have a few not so strong connections. So if you can, I mean, again, it's really back and forth with a climate scientist to say, okay, start with the most important ones and see what you get with just that. And it's really a lot of common sense and just talking back and forth with a climate scientist. What do you think are the most important variables? How would you set up, say, a model when you're simulating this? And this is usually a good guess for which variables you should be using. But start simple, and you can always add more to it. But if you throw the whole kitchen sink at it from the very beginning, and you don't even have so many samples usually, you might just get a mess. And usually test for robustness. That's always my first test. I vary some of my parameters, right? Significance values, baseline and stuff like that. And my model shouldn't change that much. If it does, it's probably just a lot of spurious correlations that happen to be in the data, and I'm overfitting or something. So it's always robustness, keeping it small if you can, and going back and forth many times. It's like, does this really answer the question we're trying to answer here?
And I guess that goes for any kind of statistical machine learning approach, right?
Exactly.
Good kind of data hygiene, I guess. And
exactly. Yes.
There's a question here from Gulson Tuscan I'd like to just explore a little bit. So the question is, how do you relate explainable AI, explaining the black box kind of things, to causal inference? And the reason that caught my eye is because for me, this way of explicitly relating these variables and the causal directions between them is very akin to what I'm doing scientifically, right? I'm trying to understand whether this thing affects that. And so for me, these causal approaches are inherently explainable, and that's one of their strengths. But I'd be really interested to hear your thoughts on that.
I was laughing about that question because Jakob and we were coordinating last night, or for me it was last night, and we were exactly discussing that question. Can we use Shapley values and see how that relates to causal signatures and stuff like that? Okay, so it's a big question. I mean, it's like, first question is which kind of explainable AI methods are you talking about? I think just starting out and saying, okay, if you say, you look at variable importance. Well, if you do first a machine learning thing and prediction, and you do variable importance, that can be a great first step to select which variables you should actually be looking at, right?
True.
But that of course doesn't tell you yet, are those, are they correlated? Which causal direction is there, and all that kind of stuff, or are they just associated? So it's kind of a good first step. But yeah, explainable AI is trying to do exactly the same thing in terms of figuring out how is, at least, say if you have a neural network, how is the neural network trying to figure this out? But you're trying to then find the strategies that the neural network is using, and not necessarily the one that your underlying processes have. So only if your model is really good, and even then you can't be 100% certain that it actually uses the right strategies. So if you use explainable AI, you may find the strategies on your network, but not of the underlying processes if you're not careful. But if you have a really well-fitting model, then maybe you can gain something about causal relationships. Jakob, you want to take a step?
Yeah, I mean, it is really interesting to me also, but I think it's not the goal of these methods, even though the words like relevance or feature importance kind of have a causal connotation, swinging with them, but they're not built to that, and they do not use assumptions. So they're not explicitly building in assumptions, which is the basis of causal discovery and learning. It doesn't come out of the data alone, and therefore I'm skeptical that I guess you come up with examples where causal relations in a toy model, and then your feature importance will give you a high relevance to some confounded feature, like to some variable that is just correlated but has no causal path to your target variable. And it wasn't the statement of the method to say that this variable here is causal. It just say it's relevant. And maybe a variable that is not directly causal related can be very relevant inside a machine learning model. So I have this one idea in mind that you have a 100-dimensional process that causes Y and also causes X. And then your machine learning model of Y trained on these processes, on this 100-dimensional process and X, might then just say, well, just use X. It's a very good representative of these large dimensional process, and it's very efficient to use it for predicting Y. So it's not causal, but it's efficient to use it, or the method used it because it better compresses the data or so. And then the difference would be that that's a good predictor if you stay in the same distribution. If you're stationary, if nothing changes, then always how this Z causes Y and also causes X then X will always give you a good prediction of Y, right? But if something changes in X because it has other causes, and so in a new environment, this will not be a good predictor, and then this will fail.
While you were talking, Jakob, I was thinking about it a little more, and I think there's maybe one way of looking at it is that if you use explainable AI, it still gives you hints, right? But maybe the hints are weaker than what you get with a straightforward causality analysis. But it can still give you hints and hypotheses that then maybe you do a causal analysis on this next, and then you do hand it on. But I do think, I mean, we do a lot of explainable AI in our lab, and I do think that you do get hints as to what causal relationships there could be for certain things.
I'll take one more clarification question. Is from Manish Jasmana. Can causal theory for time series, how does it deal with non-stationary data in time series? Do you want to take?
Yeah. So there's no magic, of course. So there's different ways. Either, like in my mind, non-stationarity has a cause. Like there's some reason why the system changes, why the distribution of the system changes, why the underlying causal relations change over time. So there's some variable, a latent variable potentially, that causes the system to change over time, like causal links to change over time, which might happen, for example, in summer and in winter, the circulation goes rather in this direction or in the other direction. And that's a variable that you may have expert knowledge about. So you may know that, okay, winter and summer are different. So I just analyze my data in winter or summer. Or you may know that, well, you know the seasonal cycle in general, and you can remove that confounder, which leads to a certain type of non-stationarity. If you don't, we have some work which tries to reconstruct different regimes of your causal dynamics. So it assumes that there's a limited number of regimes and that changes over time. And it tries to reconstruct the different regimes, but it's a more challenging problem, of course, that you need to address by using more expert knowledge. And that's my answer to this currently.
My answer would be, there are some algorithms that try to deal with non-stationarity, but I haven't seen a whole lot of it yet, and I just totally try to avoid it. It's like, you know, we have a changing climate. I cannot, you know, I have to be very careful that I choose periods in time that I think are consistent. And we actually do sometimes studies where we take 20 years here, 20 years there, 20 years there, and we see how it changed over those. But I really try to take one time series, one period of time where I think it's stationary. I develop a model for this, then I take a new one and I develop a model for this. But I would not know how to deal with one model for a non-stationary process. I break it up into pieces. Yeah. And then look how things change.
The system is hard enough, right, when it's
exactly
small chunks. So that's wonderful. Thank you very much for the talk and for a really interesting discussion. I think probably that's a good point to bring it to a close. But thank you both again. Yeah, it's been a pleasure having you.
No, it was a fantastic session. Thanks a lot and very, very instructive. Before we all run away, I should introduce also the next session. The next session is on next Wednesday, 26th of January, and it's on AI model data integration for understanding climate impacts in the Earth system. Another another set of great speakers. So Markus Reichstein, director at the Max Planck Institute for Biogeochemistry, and Michael Obersteiner, director at the Environmental Change Institute in Oxford. So tune in again next week, and we hope to see you all then again. And I hand over.
Thanks a lot.
Thank you, Philip and Duncan, and big thanks also to Imme and Jakob. We hope that you enjoyed the webinar, and we're launching a quick poll that will now be appearing on your screen. And in the meantime, we're also leaving the links in the chat. So you can find the link already to the session that Philip just mentioned there. And then more links will be appearing. We also have on January 27th, a seminar with Alex Davies of DeepMind, who is talking about their recent paper in Nature on working together with AI to make mathematical discoveries. And with that, I'd like to once again thank everybody involved. So first of all, our speakers, Imme, thank you very much. Jakob, thank you very much. And our hosts, Philip and Duncan. And with that, we hope to see you soon. Thank you.
Selector, rewind selector, rewind selector, rewind selector, rewind selector, rewind selector. Selector, rewind selector, rewind selector, rewind selector, rewind selector, rewind selector.